All right, so we are chapter 12, section 2, page 393. The solution process. The solution process. So what that is talking about is how do we make a solution and how do we change that speed of making a solution. For example, if you want to put some sugar into water, how would you get that to go faster? We're going to look at 3 different ways. Raise your hand. We could heat it up. What would heating do to make the process go faster?
It moves the molecules around faster, so it will spread faster.
Yes, the molecules have more what? Kinetic energy. So they're moving faster, so their motions are going to go faster, and therefore they're going to dissolve more rapidly. All right? They have more velocity. Okay, so that's one way. We can heat it up. What's another way?
Pressure?
Pressure actually can help, and we're going to talk about that in gases more than we will. Right now I'm kind of focusing on solids into liquids, but with gas, Ruta, you are absolutely right. We'll come back to that. Let's maybe another example. You're making hot chocolate. What are things that you do so that you get to have a nice cup of hot chocolate? You stir it. Now in our book we don't say stir.
Mix.
We say, page 394, we say agitate. You see that orange word up at the top? When you want one of your friends to do something, or you just want to get a reaction from them, you what? Agitate them. You push their buttons, right? And so it is with the solution. We're going to agitate it. So when you make that hot chocolate, what are you going to do? You're going to stir it. You're going to agitate it. All right? That speeds it up. Why does it speed it up? Because that motion that makes the dissolving process happen, you're adding to that motion, right? The particles are now moving because you are moving, because it's all about getting them to move. We want them to move. All right, so we can heat it up, we can agitate it, and there's another one that's not quite so obvious. You're making hot chocolate. Why don't they sell hot chocolate in like a lump? Why don't they put it in a chunk or a cube or something like that? It would take longer to dissolve. So, if it takes longer to dissolve as a chunk, how can we speed it up? Break it up into little pieces. All right, now this happens sometimes. Maybe you've done this before. You come walking into the classroom and you've got a lollipop in your mouth. Mr. Singer says, no lollipops in the classroom. Now, some of you would take that out of your mouth, put it back in the wrapper, and carefully save it for later. But most of you wouldn't. What do most of you do?
Crush it.
Crush it. Why does it go faster when you crush it?
There's tinier pieces.
Tinier pieces. It's true they're tinier pieces, but there's another bigger reason. What happens when we have tinier pieces? How do we get... So let's say that we have a chunk of lollipop or whatever, and we crack it in the middle. Did we just increase the amount of surface area that's available for that water to dissolve it? Yes. And what if we break it up into more pieces and break it into 1,000 pieces? What happens to our surface area? It increases a lot. Another way to think about it, let's say that I have a box and I need to paint the box. I would need a certain amount of paint, but what if I cut the box in half and now I got to paint the inside of the box too? And I cut it into more and more pieces. Would it take more and more paint? Why? Because it increases the surface area. All right, so what are the 3 ways that we can increase the speed of the dissolving process? Heat it, agitate it, and break it up into pieces, or more specifically, increase the surface area. All right. Next concept, page 394. We've talked about this in terms of evaporation. Remember we had a pot, and in the pot, the water, I need water, I don't have any blue. The molecules are evaporating, but they're also, some of the water molecules are going back in, right? So there's evaporation, but there's also, what's the other process? Condensation. If we put a lid on the pot, then that process can happen at the same rate. There's just as much evaporation as there is Condensation. That would be what? Equilibrium. Well, we can do the same thing with, I'm just going to draw a pot for fun, but let's say that we put in there some water, and in this water we put in there a chunk of salt. At this surface, are there salt molecules that are dissolving into the solution? Yes, because they have what? Kinetic energy, and they shoot off. Could it also be possible that there's a salt molecule that is running and crashes back into that salt crystal and comes out of solution? Yes. So if this solution has just as many dissolving as are coming out of solution, we would be in what? Solution equilibrium. Solution equilibrium. Kind of like this. How did we shift equilibrium? How can I shift it so more is evaporating? We could heat it up. What are some things we could do to shift equilibrium here? We could heat it up. We could add more water. You know, we could do things that will change whether or not it's dissolving or it's crystallizing. What would happen if I evaporated the water from here?
There would be less water.
Well, there'd be less water. What happens when you come back from the beach and you got the salt water and so forth and you drip it all over the place and then it evaporates? What happens?
It leaves salt behind.
It leaves salt behind. So what happens to our equilibrium? We shift it towards coming out of solution. Make sense? Okay.
Wait,
Sir.
crystallizing means what?
Crystallizing means that the whatever is dissolved is coming back to the solid, and when it does that, it likes to do it in a geometric pattern. It's kind of like it's stacking the atoms in order, and it'll form a crystal.
That won't happen in water.
Oh yeah.
Just what? Will make crystal water?
Oh, what do you mean? You mean
So this is solution.
freezing water
Like,
or salt in water?
yeah.
So the salt crystals, yeah, as the water is evaporating, the salt crystals will form.
Okay.
So this will also happen in your body. In your kidneys, your body takes water, takes the waste from your blood and so forth, and in your kidneys is trying to get rid of that. If you drink lots of water, your body doesn't have to take the water back out. It can leave it in there and wash that out of your body. Look at me now, you guys. This is one to pay attention to. So, as that you drink lots of water, whatever's in your blood or in your kidneys can stay dissolved and you can pee it out. But when you don't drink enough, your body has to say, oh, we can't afford to lose the water, so we're going to put the dissolved stuff in there, and now we're going to take the water out. What's going to possibly happen in your kidneys? It'll form crystals, and we call those kidney stones.
My dad had that.
Did he?
Yeah.
I'm so sorry. How many of you know somebody your age that has had a kidney stone? Anybody? You have three? Yeah? That used to be unheard of. Teenagers never got kidney stones. So why is the teenagers can get kidney stones?
We're eating all this stuff.
It's sodas and stuff. We are eating so much worse that diseases and problems that people might have gotten at 40 and 50 and 60 years old because of some poor habits, we're now getting at 17, 18 years old because we are eating so much junk so much more often that we're getting some of these problems. So I have not had it happen to me, but I understand it's more painful than childbirth. Kidney stones. Notice they're not called kidney pebbles or kidney sand. What are they called? Yeah, they might be thinking kidney boulders. Okay, so you have a little tiny tube that comes down from your kidneys. It's very small. And when the crystal starts going down that, it hurts so bad that you're sure that the rock must be this big. All right? Very, very painful. It can actually cause bleeding, and you can have blood in your urine. It can be very, very, very miserable. It'll put you in the hospital. It can. All right? Or you might wish you were dead. It's very, very painful. So how can you avoid kidney stones?
Water.
Lots of water. What should you avoid drinking? Soda, especially which ones? The brown ones. So the Coke, the Pepsi, and so forth. Caffeine. Okay, so coffee. Kidney stones is a famous one for coffee drinkers. All right, and have you heard that coffee is a diuretic? What does that mean? Makes you have to go to the bathroom. Well, why do you think you have to go to the bathroom? What is the reason why you have to go to the bathroom? Your body's getting rid of waste. So why is it that coffee makes you have to go to the bathroom?
It's just bad stuff.
It's just bad stuff, and your body says, "Oh, I got to get rid of it." Okay? Don't. If anybody tells you coffee's good for you, just politely listen, and then know that they are wrong. Coffee is bad on all levels. There is no good thing about coffee. There's no good thing about caffeine. And a lot of you are looking at going to college soon, and you're going to feel like, I got to stay up and study. Coffee is not the way to do it. The way to study is to go to bed and get your rest. Do you know what is unique about today? Daylight savings. Did you know that more people will die today of a heart attack than any other day of the year? Yep. And did you know what day of the year do the fewest people die of a heart attack of the year? It's in the fall. Okay, where we have an extra hour of sleep. How important is it to get your sleep? It's really important. Mr. Singer cannot convince you enough to get your sleep. Caffeine is the destroyer of your sleep and your brain and your health. Don't do coffee. All right? It's become such a cool thing to do, and that's just your go-to. Does the coffee actually increase your brain function? No. In fact, if you are tired and you're driving, did you know that once you're tired and you're trying to stay awake, your reaction time is about the same as a person that is legally drunk? So if someone jumps out and starts walking in the crosswalk or something, and you need to hit the brakes, your reaction time is similar to someone that is legally drunk. If you drink coffee, you may feel like you're more energetic, but guess what? Your reaction time is not any better. You're going to probably drive over that person in the crosswalk, just like a person that's drunk. Okay? So, anyway, enough on that. Don't do coffee. It's not good for you. All right. Yeah.
Increase our brain function,
Yeah, so tonight, go to bed early.
Why can't I go to sleep?
You can't.
We have a test.
We have 2 tests to do.
You know what? The more you need to do, the more you need your sleep. It's true.
When
It's true.
Okay, when do you suggest us to go to sleep? What time?
Okay.
Give us our schedule right now, Mr. Singer, what we should do.
All right. So you may not believe this, but we had 4 boys go through this school.
Okay, no way.
Okay, 4 boys. All 4 went to bed between 9 and 9:30 every night, and got up about 6:30 or 7 in the morning. Okay, so they were getting 8 to 9 hours of sleep every night, and they all got top grades.
And they woke up at what time?
6:30, 7 o'clock
To study.
to get up, get ready for the school day, and so forth. So
And when do they study?
they studied what they needed to.
No, but
When they got home,
What time of the day?
when do they get home?
in between, most of them didn't have any free periods. They were either in school or working until school was out. But when they got home, eat supper and they went and did their homework, and then they went to bed.
Okay, but like for how
So-
long? When did they get to school? Get home? They went home at like what, 5? And it's 8.
Yeah, they
and
came home for
6?
supper. Yeah, so 5 o'clock they were home.
That's only 2 hours of study. If they go to sleep at 9.
Guess what? When you have your sleep, you can do it, and you can do it quickly.
But 2 hours is like what I need for chemistry. But if I didn't have chemistry and then the other classes, I need like at least 7.
So most of it,
I'll try this out for a week.
my friends, is time management. Most of it is time management. Budget your time. If you have gotten your rest, you will be able to do your homework faster. Yeah.
What if you have an RA job and you can't go to sleep till 10:30?
Real.
To be honest, I would quit my RA I need my sleep. If you can't get your sleep,
I can't quit. I can't quit. I want my alone room.
I was an RA too, in college, and I eventually quit my job because I needed my sleep. And my freshman and sophomore year, I stayed up late, I was miserable and tired and so forth all the time. My junior and senior year, I said, forget it. I'm getting my sleep, and if I'm not ready for that test, I'm still getting my sleep. And you know what? My grades went up.
No way.
Yep.
No, but you know, I'm gonna try that, Mr. Singer, and if my grades go down, I'm gonna cry. I'm gonna be like, Mr. Singer.
But it's also about time management. It's not like, oh, I'm going to play video games and watch movies. Oh, it's bedtime. I've got to go to bed and not do your homework.
No.
It's about time management. Okay, you do your homework when you can do it. All right, got a few things left to share with you.
That's my goal, Mr. Singer, try.
You can do it. I promise you it works. I've seen it in my life, and I've seen it in our boys' lives and many others. Get your sleep.
What if I trust you and I do this for a week and my grades like
Yeah, that's what I'm saying. Can I just have like a test run week and then
Get forgiveness afterwards.
Yeah, and then if it goes south, then can you just like cancel that out of my grades?
You know, I'm not able to do that for you, but I do know it works. I know it works. All right, let me finish up with your chapter. We can talk more.
What if we thrive at night and that's actually just...
All right, let's come back to the solution. Come back to this solution. Let's put a chunk of salt in here and let it sit there until it is dissolving just as fast as it's coming out of solution. We're at equilibrium. At that point, this solution is, what's the word in your book? Top of page 395. Saturated. So this is like a paper towel or a sponge that you put in the water and you can't soak up any more water. That sponge is saturated. So we can have a solution that holds as much as it possibly can, then that solution is saturated. True or false? Water will dissolve just as much sugar as it will salt.
False. True.
Will it dissolve the same or both?
False.
It's false. It will dissolve a ton more sugar than salt. All right, now it'll dissolve a lot of salt. You can go to the Dead Sea and so forth, and you can float lots higher in the water because there's so much salt that the water becomes more dense. But sugar, you can dissolve more sugar in water than there's water. It's unbelievable. If you buy a can of condensed milk, which shouldn't be renamed as dissolved sugar, it's almost like a thick syrupy stuff because there's so much sugar in that condensed milk. Water can dissolve. So, not everything dissolves the same. In fact, everything dissolves differently, and we have a solubility table. If you turn to page 396, there's a whole bunch of different substances there. Do you see near the bottom NaCl? Yeah. And then there's temperatures. Kind of like you said with the hot chocolate. Can I dissolve more if it's hotter?
Yes.
Yes. So look at salt. You know, at 0 degrees freezing, we can dissolve 35 grams. And then all the way up to 100 degrees, we can go clear up to 39. Okay, that's a little bit more. But go up, the third one from the top, that's sugar. At 0 degrees, how much sugar can we dissolve? 179. Compared to salt, that's like 5 times as much salt. And when we get up to 100 degrees Celsius, look, it dissolves up to almost 500 grams. And by the way, how much water is this? Look at the green at the top. How much water? 100 grams. How many grams of sugar can you put in 100 grams of water? Almost 500. You can dissolve so much sugar in there, whereas salt is barely 39. Okay? All right, let's go back to page. Now, let's say that we just drop this salt in the water and it just starts dissolving. What is the word that is the situation now?
Unsaturated.
Unsaturated. So I've got a sponge, got a little bit of water on it. Could I put more water in it? Yes, that is called unsaturated. All right? Same thing, if it can continue to dissolve, it's unsaturated. Now, there's an interesting situation. Let's say that I heat up my water to 100 degrees and I dissolve all the salt or sugar in there that I can. But then I take it off the heat and I cool it down to 0. So it was saturated and now I cool it down. What's the situation?
Does it get out of
More saturated?
Now, if I have a crystal in here, it will then shift equilibrium so it will come out of solution and form more crystal, right? But there's a really cool thing. What if I don't have any crystal in there. And it's all dissolved. It was saturated. Now I cool it down. Now all these particles here say, you know what? We want to come out of solution, but we have nowhere to go. We call that a nucleation point, a starting point. It's like a foundation. We have to have a foundation. If we don't have a foundation, it won't come out of solution. So if it wants to come out, but it can't, what is that called? Super saturated.
So what's the nucleation point?
Nucleation point is a starting point. So let's say I have all this here, and I cool it down, so it's now super saturated. I can drop in here one crystal, and guess what happens right there? They'll all start to go on this right now. And we're going to do this in lab. It's one of my favorite labs.
Sugar crystal?
We're going to do it with a different substance. Sugar won't work very well, but there's some that will, and it's really cool.
We should do it with sugar too. You know, like the rock candy.
Yeah. Sugar is so soluble, it's very hard to get it to come out of solution. So you have to, I've done it before and it takes forever, and then you get dust in the air and nobody wants to eat it afterwards. It gets kind of gross, but what? You want to try it? We'll just give you some sugar cubes. Yeah.
So I still don't understand how it's possible that a solution can have more than it can have. Like, how does that make sense? A super saturated solution.
Yeah. Well, that's exactly what happens is we can dissolve it, and then we say, okay, we drop the temperature, and it says, we don't have enough energy to keep you in solution, but we have nowhere for you to go.
So it's just
There's-
there.
You're homeless. There's nowhere for you to go to sleep,
So what
so
happens to it?
it stays in solution.
But
And so it's super saturated.
Wait,
But if we create a position for this to start,
it's gonna.
it will start instantly.
wait.
So, okay, do you guys remember when we did the test tube and I said save a crystal out?
That's what I was.
Oh, you were gonna say it? What are you gonna say?
I was like, cause like, when we dropped it below like the freezing temperature, but there wasn't any crystal for it
Right.
to freeze, it would stay liquid until you drop that crystal and
That's right.
everything freezed around it.
Okay, so that crystal was your nucleation point. All right? So if you don't have a place for it to start, it'll go below freezing and it won't freeze. And Noah's going to say, but I don't understand how it cannot freeze. It has to have a place where it can start to form the crystal. You have to tell it how to start stacking. We want to know how to stack these little atoms to make the crystal. We want to know how it's done. But if nobody shows them how it's done, we can't stack them.
Could you just put anything in there? Like a stick and then start to attach to the stick?
The answer is very likely, okay? In fact, if this container has a scratch in it, it'll start at the scratch. All right? Back to the freezing and the boiling. One of my best friends graduated from here. He went to Berkeley, I went to PUC. And we were both taking organic chemistry. And at Christmas time, we were talking to each other, and he was, in Berkeley, the lab, when we do organic chemistry, at least once or more, somebody always blows up their lab equipment. It's like, whoa, you guys blow up your lab equipment? As we were talking about it, I figured out what the problem was. You see, they were using brand new glassware, and in here they're boiling the water, but you see, in order for boiling or freezing to happen, what do you have to have?
Nucleation.
Nucleation point. When you have a new piece of glass, there's no scratches in there. There is no, and if you use distilled water, there's no dirt in the water. You know that it won't snow or rain unless there's dust in the air? It has to have a nucleation point. So my friend was at organic chemistry, and they're doing these labs, and they're heating this up, and the water gets super hot, 100 degrees, 110 degrees, and it's not boiling. And then, somehow, a little piece of dust or something like that falls in here. Whatever the point is. And it finally says, oh, we can turn into a gas. And as soon as one does it, what? And when they do it all at once, guess what happens? They explode. So at PUC, they told us you have to put in here little chunks of ceramic, broken ceramic. Why do you think we put ceramic in the container? Create a nucleation point. So off of these ceramics, you would see these little bubbles coming off here as they're boiling. We never blew up our equipment. So I told them, well, you go tell those smart guys at Berkeley, just put a little little bit of ceramic in there, and nobody has to blow up their equipment. Yeah.
So when you're cooking with the new pot, you have to stretch the pot for you to be able to boil the water?
Yeah, your pot probably, since it's made out of metal and it's been, glass is super smooth, okay? Metal, they have machined that, and so there's probably going to be small enough points for it to. If you put just salt in there, have you been boiling, get water boiling and it gets really hot and you throw the salt in and go shh?
No.
A lot of bubbles all of a sudden form because you just created a bunch of nucleation points. Now, as soon as it dissolves, no more nucleation points. But when you put it as a crystal, nucleation points, it'll boil a bunch all of a sudden. So be careful. If your water is near boiling and then you throw salt in there, you could get a bunch of boiling all of a sudden. All right, so we could be unsaturated, we could be saturated, and we can be super saturated. Now, how much can be dissolved is on the top of page 396. That was that table. How much salt or sugar we can dissolve, that is called what? Solubility. Solubility. That's the amount that we can dissolve. Every substance, every solvent, and every solute has a different solubility. That's why they have big tables and so forth. Do you have to memorize them? No. Any of that information will be given to you. Now, the next part, it's actually titled, I would circle it, highlight it, maybe somebody else has done this in your book, 396, the orange part that says like dissolves like. You see that? Like dissolves like. Have you noticed that sometimes the people that hang out together like the same entertainment, the same, maybe they like sports, maybe they speak the same language and so forth. Is that a bad thing?
No.
Let's just be honest. That's okay, right? Another way we say it in English is birds of a feather flock together. It's that way in chemistry, all right? Like dissolves like. So if we have some water, which is polar, water is polar, what kind of things will dissolve in polar solutions?
Polar.
Other polar. What else?
COVID?
Ionic. Polar and ionic will dissolve in there. So what's the other option?
None.
Non-polar. What? Give me an example of something that's non-polar.
H2. No.
Yeah, it isn't, but it's not a good liquid to talk about. Oil would be a mental one that's a little easier to think about. Yeah, H2 is non-polar. But oil is not polar. Does it mix with water?
No.
Because they're not like each other, are they? So they don't mix. Well, other oils like nail polish, will that dissolve with the nail polish remover? Yes, because it is like that. They're both non-polar. But will nail polish come off in water? No. Not really. Okay, because it is not like. So we're always looking for things that are similar in chemistry to dissolve with each other. Does that make sense? Have I done the dry erase thing here where I write it with a Sharpie on here?
No. Oh, I know Sharpie's not.
You know what I'm talking about? So if I take a Sharpie and I write on here like that, and I can't erase it, right? Now this is, you guys remember we did the little paper here? This is what? Non-polar. Did it go up with the water? No, because it is not alike. But, even though this is not the same, this is also non-polar. So I can do this. And we'll dissolve it away.
We learned that from being an RA in our boards.
Did you?
Yeah.
Yeah. So, why does this work that this marker can take away this marker? They're both non-polar. Could I use water to do that? No, because water is polar and it won't do it. So I have other markers. These are water-based, and we could use water to dissolve these. Those are the ones that you used on here. Okay? That's why we did it that way. Okay, now, running out of time. Page 397. Hydration. When we say, I see a lot of you guys have water bottles. What does it mean to say you're hydrated? You have plenty of water. All right? Speaking of IQ, if you are thirsty, your IQ is down 10 points. So, if you want to increase your intelligence, keep your brain with plenty of water. Not to mention food and things like that. All right. In chemistry, when we say a hydrate, and this is going to be easier if you look in your book, okay? It's kind of a weird bird, but water will chemically bond with other substances without becoming part of the substance. Does that make sense? So they kind of bond, but they're not really bonded. And they form a hydrate. The most famous is the porcelain plaster of Paris. This is where maybe in kindergarten they gave you a pie pan and they put some stuff in there and you put your hand in there. Did anybody do that in kindergarten or ever put there and make a permanent print of your hand? Take a piece of pie and put your hand in it, take it away and make a print of your hand. It's permanent. It's hard. It gets hard. Anybody do that? Yeah? Okay. That is plaster of Paris. That is a hydrate. So you take this powder and you put some water in there and the water will actually bond into a crystalline form, kind of like they show you in your book here. It's a hydrate. Yes?
So it's like cement.
It is like cement. Yeah. It is not cement though. But it's like it. But we can reverse the process. So if we can add water, kind of like this, can we add water here? Yes. Could we reverse the process? And the answer is yes. So you can take a hydrate like this pie pan that you put your hand in. We can put it back in the oven and heat it up and reverse the process and your hand is not going to be there anymore. All right? We'll turn it back into a powder. You've all probably bought something that has a little package in there that says silica gel, do not eat. Anybody? Yeah? Okay. That is that's the anhydrous. An meaning what? Prefix an means not, right? So anhydrous means what? Not hydrated. So you get this little packet in there and it says silica gel, do not eat. It is anhydrous. Why do they put it inside that stuff that you're trying to buy? Your cell phone or whatever. What?
Keep it from getting wet.
Yeah. So any moisture that comes into that package, what's going to happen is it's going to go to that silica gel and turn into a hydrate. So it's anhydrous when they put it in there. By the time you bought it, it's sort of hydrated a little bit from the air to keep it from getting into the product that they're trying to sell you. That is a hydrate. There are lots of hydrates. We're going to do one in lab tomorrow. You're going to take a hydrate and you're going to make it anhydrous. You're going to heat it up and make the water go away. And we're going to measure how much water was in there. And you're going to actually figure out the chemical formula for this hydrate. So it's a crystalline pattern, and they write it kind of weird. Look in your book. You see where it says figure 2.6? Right there in the middle.
Yeah.
And then right below it, you see CuSO4
Oh, yeah.
dot 5H2O. Now, in your life, in math, you see a dot like that, what do you think? Multiplication. That's not what this is. This is just their way of saying we have the anhydrous thing with what? Water, and now it is hydrated. It tells you how many waters surround this thing. 5 in this example. It could be 2, it could be 7, it could be a bunch of different numbers. It depends on what it is. Okay. We'll squeeze in the last little bit of words here. Things that do not dissolve on page 398, like water and oil, we say that they are what? Immiscible. What does the prefix im mean? Like impossible. Means not. Okay, so immiscible means what? Not. Okay, so there's a couple of things I'll need to tell you tomorrow. We are going to do a quiz tomorrow, section 2.